Okay, so now we're going to look at something called displacement, and it's important to realize that the calculations to do with displacement are often the ones that people struggle with in the numeracy exam. So really important that you understand the principle, which is sort of quite simple really, but as I say, it is important you understand it. So let's talk first of all about displacement values, because these are often the way you will come about displacement. So the definition there says that displacement volume is the quantity of solvent that will be displaced by a specific quantity of solid during the dissolution. This means how much space does something take up, really. So the volume of the solution that's going to be occupied by the solute. So when you put something into liquid, you'll be familiar with the idea that it might overflow. Imagine getting into the bath. If the bath is full, and it will overflow. So that's really the same principle. And some of us, I guess, have more displacement value than others. So if we look at this, same idea here, that if you put a solid into a liquid, that the level of the liquid is going to go up. And this is the principle that's involved. Obviously the values are often very different. The amounts of water or solute that will be displaced will be quite different. So we're going to talk first of all about displacement volumes involving solids and liquids. So let's imagine, for example, we've got methicillin, which is a antibiotic, and we have to add water to it to make it into an injection. Now, what we're told here is that the methicillin powder has a displacement volume of 0.7 mils per gram. So for every gram that's given, the methicillin powder will displace 0.7 mils of water. Again, just get that concept in your head. So we might be asked the question, calculate the volume of water for injection required to produce 1 mil of an injection containing 5 milligrams of diamorphine. Now we need some more information, and one part of that information is we've got a vial containing 5 milligrams of diamorphine powder, and what we need to be able to give is 1 mil of injection. Now clearly we can't put 1 mil of water for injection in there, because that would be more than a total volume of 1 mil, because it contains the 5 milligrams, but we don't know by how much more it will be. So to help us, we now know that the displacement value is 0.06 mil per 5 milligrams. Helpfully, it's given us the amount per 5 milligrams. Often you'll be given per 1 milligram and have to work it out, but in this case it tells us that for every 5 milligrams of diamorphine, that the amount of space that takes up is 0.06 mils of water. Remember, milliliters are a measure of volume, of the amount of space. So for every 5 milligrams, it takes 0.06 mils. So how do we go about this? So we know that we need to end up with 1 mil. The displacement volume is 0.06 mils per 5 milligrams. So therefore, 5 milligrams of powder will take up 0.06 mil. So we just, in this case, just simply take it away from the 1 mil. So 1 minus 0.06 gives us 0.94 mils of water. And that allows us to know that we've got the right amount of water there. We may come across different issues where we've got displacement volumes with solids incorporated into other solids. Remember, It's not so obvious when you add two powders together, but they will have different densities. So solids have different densities. So that solid will occupy a volume in the other solid as well. And that may be quite different depending on the nature of the two solids that you're putting together. So solids have different densities. And the major area where this comes up with pharmacy is in the preparation of suppositories and pessaries. There's a particular reason for that. So making a pessary, basically a pessary is designed to be inserted into the rectum. The way it works is that it dissolves, allowing the drug that's incorporated into it to be absorbed through the rectum. And these are, the drug will normally be put in a sort of a base, which is an aqueous glycogelatin type base, which dissolves at body temperature. So we need to know how much of the drug to use. Now the important thing about this is that the size of the suppository is the same. It doesn't matter which drug or base you use. You have a suppository mold is actually made to be a certain size, and the size of the mold, as you can see here, is fairly uniform. Just trying to get the pen to show us this. So these molds are made a particular size. We have our base, which we use, which we dissolve down and we pour into these molds. But you can see they're actually a certain size. And as I say, that size doesn't change. So what we have to do is to be able to fit in the drug into this base in the right amount, so that when you come out with the volume that's the same size as the mold, when the volume of product you've got is the size of that mold, you've got the right amount of drug in there. Again, you might have to kind of keep thinking that through before you actually get the what the concept is. So the base is mixed with the drug, but they will have different densities. Okay, so if we think about this, and now this is where it gets often a bit complex. So a drug with a low density will displace more of the base than a similar weight of a drug with a high density. So if you imagine that you have a kilogram of iron in one hand, and you've got a kilogram of the polystyrene packing in the other hand, you can imagine that the polystyrene packing, there'll be a lot more of it, a lot more volume of it than there will be of the iron. So this is the principle that you're working on. And so what that means is that if you want to get more of the polystyrene, or the same amount of polystyrene, same weight of polystyrene into a particular volume, then it's going to displace much more of the surrounding area than the iron would. So imagine putting them into a bath. You'd need a lot more space for the polystyrene than you would for the iron. Now what's happened is that over the years they've worked out a lot of displacement values, and these are the weights of drug that would displace 1 gram of suppository base. So those are displacement values. So it's really important idea, this idea of the fact that it's the weight of the drug that would displace 1 gram of suppository base. So each suppository base is different, so they'll have different displacement values for different suppository bases as well. So for example, that we're given here, the displacement value of zinc oxide is 4.7. So what that means is that 4.7 grams of zinc oxide will displace, or take the place of, occupy the space of 1 gram of the suppository base. So therefore zinc oxide is much more dense than the suppository base. By contrast, menthol has a displacement value of 0.7. So therefore 0.7 grams of menthol will displace or occupy the space of 1 gram of the suppository base. Therefore menthol is less dense than the suppository base. So think of menthol there as the polystyrene packing and the zinc oxide as the lump of iron. Okay, so it's the menthol will be that much less dense. So we have to use those displacement values to calculate the amount of suppository base, because we know that we want a certain amount of drug and that we've got a certain volume of base of suppository that we can have. So we may be given questions where we have more than one medicine in the suppository. At the moment we're not going to cover that. Let's cover the basics first. So we're going to look at that in the second part of this lecture.